it's my pleasure to talk about this a particular point from Christina's previous talk on related to the prism inequality she mentioned. So I would like to discuss a little bit of the background history and some current development of the so-called dihedral rigidity phenomenon of Riemannian polyhedra. Okay, so let's start. So I think one major motivation that Gromov studied this kind of polyhedral comparison goes back to the weak notion of curvature lower bounds, and in particular comparison theorems that people usually use to define these weak notions of curvatures. So for sectional curvature, that's classical, right? We do it by triangle comparison. And this nice picture is taken from Cedric Villani's famous book, Optimal Transport. Well, essentially, it's just the saying that if two spaces has a comparison pointwise on their sectional curvatures, then the geodesic triangle. Sorry, I should have said, well, if a space has a sectional curvature lower bound, then this curvature lower bound condition is equivalent to the fact that all geodesic triangles are fatter compared to the corresponding geodesic triangle in the modal comparison space. And people use this triangle comparison phenomenon or theorem to Topononkov theorem to define the so-called Alexandrov space. Okay, so that's how the sectional curvature lower bounds was achieved for metric spaces. And similar stories for Ricci lower bounds was done via pretty different approach using optimal transport and a lot of related Chigger coding and neighbor theory. And they're also done by comparison theory, but it's kind of far away from our story today. So let's just skip that. So the question comes to how we define scalar curvature lower bounds. Let's say R bigger than or equal to some constant C. Okay. So the question is that then can we verify these scalar curvature lower bounded by C by, for instance, measurement with the metric, or at least not without taking too many derivatives on the metric tensor? Well, Gromov's beautiful answer to this question is yes, and this can be done by comparing Riemannian polyhedrons to those in modal spaces. So the first example that he proved is the following. So for simplicity, let's just state the theorem for 3 dimensions, and actually this theorem was proved for all dimensions actually. So you take a cube. Well, a cube is just, topologically the Cartesian product of the interval with itself 3 times. And suppose G is a smooth Riemannian metric on it. So this means that, you can extend G to be, in a slightly larger neighborhood. Think of M, this cube can be embedded in a slightly larger smooth manifold, and the metric G is the induced metric on a smooth manifold it's the induced smooth Riemannian metric from the larger ambient space. Okay, so then the following 3 conditions cannot happen simultaneously. So first of all, the scalar curvature in the interior of the cube is positive everywhere. And the second condition is that each face, namely the smooth portion of the 2-dimensional boundary, is mean curvature convex. Okay. Then the third condition is that the dihedral angle of M between adjacent smooth faces is everywhere acute. Okay, so these 3 conditions are not compatible with each other. All right, so to illustrate what this kind of theorem is saying, let's go back to maybe the 2-dimensional case and take a quick look. Okay, so in the 2-dimensional situation, we have a square instead of a cube. And then you have a smooth metric on it, and scalar curvature on a 2-dimensional manifold is just twice Gauss curvature. So you're saying in the first condition that its Gauss curvature is positive, and then mean curvature on boundary is just the geodesic curvature on the boundary in this case. And then dihedral angle between the faces corresponds to the the interior angle along the four corners. Okay, so the condition simply saying that K positive, Gauss curvature positive in the interior and geodesic curvature on boundary being positive, and the interior angles are acute everywhere, this cannot happen. Well, indeed, this can't happen because it violates the Gauss-Bonnet theorem, right? Because if you integrate the Gauss curvature and the plus the integral of the geodesic curvature and sum the exterior angles, you should get 2 pi. But as you can see, these three conditions here will violate this Gauss-Bonnet. Okay, so this is a very nice extension. So the Gromov theorem is a very nice extension of the two-dimensional simple Gauss-Bonnet argument. And this motivates the following notion, let's say weak notion of R non-negative. So a good way to visualize it is that in Rn, the theorem tells you that you cannot deform the faces of a cube. It's a special case to be convex while keeping the interior dihedral angles acute everywhere. Okay, so this is because of course Rn has 0 scalar curvature. On the other hand, if you allow negative scalar curvature in the interior, then you could expect that such a counterexample will happen. So in particular, in the hyperbolic space, there exists a cube, namely topologically, it's just the product of the intervals, as illustrated in this picture. So each of these cubes are with totally geodesic faces, for instance. And since you're living in hyperbolic space, you can make the dihedral angle strictly acute. And then once you have such a cube, you can imagine that by pushing outward a little bit of its faces, you still you make every face strictly convex, but the dihedral angle, although you just barely increase it, it's still acute. Okay, so so the fact that there exists such a cube with convex or mean convex faces and strictly acute dihedral angle should be an indicator, in some sense should be equivalent to the fact that somewhere inside the scalar curvature is negative. So this is as mentioned by Christina earlier, this is a proposed notion of scalar curvature non-negative for C0 metrics. So C0 RG is non-negative. Let's say we would define RG to be non-negative if and only if there does not exist cubes with mean convex faces and acute dihedral angles. Okay. All right. So this is the theorem and its importance in understanding scalar curvature. And the original Gromov's proof relies on a beautiful symmetrization procedure. So basically, you can just reflect and double the cube across each of these directions, each of the faces, and then reduce the question to the torus rigidity theorem. On the other hand, it does use the fact that the cube is the fundamental domain of a Z reaction on R3, where in n dimensions is the fundamental domain of a Zn action on Rn, and it does not characterize the rigidity case. Namely, in this case, what will happen if you change the strict inequalities to non-strict inequalities? Okay, so thus he posed the following so-called dihedral rigidity conjecture. So essentially, the conjecture just says that some analogous comparison theorem should hold for other n-dimensional polyhedrons. And I think for geometers, for me, an important type of polyhedron are the n simplices. Okay, so they are the simple building blocks of of smooth manifolds. And then there should also be a rigidity phenomenon. For instance, for a cube, this rigidity phenomenon should be something like the following. If you assume that scalar curvature is non-negative in the interior, and you assume each face is weakly mean convex, and then you also assume that the dihedral angle is everywhere non-obtuse, then this whole Riemannian cube should be isometric to a Euclidean cube. Okay. Okay, then of course you can also formulate this rigidity conjecture for other polyhedral types like a prism or a simplex. Okay. All right, so this is basically the theorem that we will talk about in this lecture. So let me maybe tell a little bit about what people know at this moment and what I was able to do in this direction. So a simple family of polyhedron are called prisms. So by prisms, I just take a planar polygon P. It's let's say a plane convex polygon, and let's take the Cartesian product of P0 with some interval raised to n-2's power. Okay, so this is a simple product, a polyhedron with a product structure. It's slightly more general than cubes, and then if the interior angles of P0 are all non-obtuse, not larger than pi/2, I'm going to call this product P a non-obtuse prism. Okay, so there are some pictures. So on the in the right here, so this is a prism. You can see it's a quadrilateral cross with an interval, and of course we also have simplices, which they're just the Euro notion of simplices. All right, so essentially what I can prove is that the dihedral rigidity conjecture holds for certain three-dimensional simplices and prisms, and for n-dimensional non-obtuse prisms between dimensions 4 and 7. Okay, so let me maybe state it precisely for these prisms. So suppose we take an n-dimensional non-obtuse prism. And suppose, so this P is then the Euclidean comparison model. And suppose you have a Riemannian metric MG that admits a polyhedral diffeomorphism to P. So that means it's a diffeomorphism that maps any K strata to K strata. Then assume that the scalar curvature non-negative in the interior and boundary mean curvature is non-negative. And here in the third assumption, I'm going to assume that the dihedral angles are everywhere equal to the Euclidean constant dihedral angle along edges of M. Then the Riemannian polyhedron should be isometric to a flat polyhedron in Rn. Okay, so and any quick question about this statement? All right, so let me mention some remarks on this theorem. So first of all, my approach would enable one to prove the theorem for slightly more general Riemannian polyhedrons, namely those ones which admit a degree 1 polyhedral map to P. So a basic example to keep in mind is that I don't need the MG to be, for instance, in the case of prism, I don't need M to be diffeomorphic to the product P0, two-dimensional plane polygon times the interval raised to a power. In the interior, you can add handles and make connected sum with other manifolds. This is allowed, but still you have this rigidity phenomenon. Okay, so the statement in general is that if you have a degree 1, if you have a Riemannian polyhedron which admits a degree 1 map to a Euclidean comparison model and satisfies the scalar curvature, mean curvature, and the dihedral angle assumption, you're going to be isometric to some Euclidean polyhedron. And the second remark is that, of course, you see these dimensional restrictions, and this comes from regularity theory of certain free boundary minimizing hypersurfaces. And when n is bigger than 3, you also notice that I need this, I believe, technical condition on the fact that the prism is non-obtuse. So this non-obtuse condition is made here to guarantee some regularity properties of elliptic equations. Okay. Again, I still believe this kind of non-obtuse condition is technical, and of course we all sort of believe that the dimensional restriction for minimizing hypersurfaces is also technical. Okay. So for three-dimensional simplices, the proof works for, I mentioned that it works for certain three-dimensional simplices, and particularly they work for those simplices that satisfies that such that you can find a phase, certain phase, where the dihedral angles, so the three dihedral angles along these faces are all non-obtuse. Okay, so previously, once I thought this is kind of condition that's satisfied by all three-dimensional simplices, but apparently I was wrong, and there are, these examples where you can find such a single phase where along which all the dihedral angles are non-obtuse. Okay, but this is the condition that I need. Okay, and Gromov also had this very nice idea of banding construction. So his banding construction essentially says that along the intersection of two hypersurfaces, let's imagine these are the two faces intersecting along an edge. What you can do is that you can bend one face into the interior a little bit. So let me maybe draw a picture like this. Okay. By doing this banding construction, you can always increase the mean curvature of these two hypersurfaces, right? Because you're bending inward, and on the other, and at the same time, also increase the dihedral angle. Okay, so in other words, heuristically, the following is true. Suppose we have a counterexample to the conjecture where you assume to start with, as your assumption that the dihedral angles is everywhere less than or equal to the constant dihedral angle of the Euclidean model. Then by doing this construction, you can make the dihedral angle precisely equal to the Euclidean model, while also increasing the boundary mean curvature. So so with this construction, then one can weaken the assumption 3 here that I assumed everywhere equal to everywhere on the dihedral angle to everywhere less than or equal to the Euclidean model. Okay. All right. So and the fifth remark I want to make here is that recently Wang Xianyu, Yu Bing, Guoliang Yu here have studied. Sorry, I misspelled this word. Have studied the question with spinors. So like many other questions in scalar curvature, there are usually two parallel paths to study it, right? The minimal surface path and the spinor path. And apparently, people have tried to study this particular dihedral rigidity conjecture also using spinors, and they have some very nice results. Okay, so so as you can see, I need to make a lot of simplifications and assuming non-obtuse dihedral angles, and also some technical conditions on dimensions and on the combinatorial on the comparison model. So I would like to believe that this feature, this kind of restrictions or additional assumptions feature the fact that analysis on this kind of singular spaces are in general is kind of difficult. On the other hand, as Christina mentioned, we do like to have a clear understanding of such a prism inequality or this dihedral rigidity phenomenon. Particularly because it has relations to these various questions. And in addition to the questions that Christina mentioned earlier, I would like to talk about some extensions of the conjecture and its relation to other interesting problems. So a first interesting direction is that it seems that we can also extend this comparison theorem or this conjecture to the case of negative scalar curvature lower bound. So namely, you assume R is larger than or equal to K, where K is a negative real number. So for simplicity, I'm going to assume K is minus n times n minus 1. Namely, it's the scalar curvature of the hyperbolic space. Okay, so in general, you can just restate this theorem by scaling. Okay, so to state the theorem, let's recall that the hyperbolic metric has a particularly nice expression in this choice of coordinates. Namely, you can write it as dx1 squared plus e to 2x1 and times the dx2 squared plus up to dxn squared. So in this coordinates, there are the coordinate functions are kind of special and nice in their way. So in particular, the x1 equals to constant planes. So the x1 planes are isometric. So intrinsically isometrically Euclidean with the induced metric, right? Because if you take x1 equal to constant, then it's just isometric to Euclidean metric. Then, and also extrinsically, these x1 equal to constant planes are totally umbilic with constant mean curvature n-1. So they are called horospheres, and I believe this is one of the reasons. And if you take j at least 2, then this xj equal to constant planes are totally geodesic. Okay, and each of these planes, x1 equal to constant and xj equal to constant, are orthogonal to each other. Okay, so the following theorem is based on discussions in the IAS workshop in 2018. So the theorem would like to raise a comparison principle where rigidity, dihedral rigidity conjecture for which models on polyhedron in hyperbolic spaces. So in particular, let's take an Euclidean polyhedron such that the dihedral rigidity conjecture holds. Okay, so as part of the assumption, we assume P1 is a comparison model in a Euclidean space of one dimension lower, where the previous theorem modeled on P1 works. And let's take P to be a product of an interval with P1, and but instead we're going to view it as a parabolic prism living in the hyperbolic space, and this 0, 1 factor is on the x1 axis. Okay, so then let's assume dimensions between 3 and 7, and let M be a Riemannian polyhedral, which admits a polyhedral diffeomorphism to this comparison model P. And in this case, we're going to denote. So maybe let me draw a picture here. So this is the P1, and you have M like this. Okay, and then we're going to call the top surface Ft, the bottom surface Fb. These two are kind of special surfaces because in the hyperbolic space, this top guy has mean curvature equal to n-1, and the bottom guy has minus n-1. Okay, and all the side faces are totally geodesic if you still remember. Okay, so assume your Riemannian polyhedral satisfies a similar comparison object, namely scalar curvature in the interior is bounded below by the constant scalar curvature of the hyperbolic space. And the boundary mean curvature should be larger than or equal to the corresponding ones on the comparison model. Okay, so it's bigger than or equal to n-1 on top, bigger than or equal to minus n-1 in the bottom, and everywhere on the side faces is non-negative. And still, let's assume that the dihedral angles are everywhere equal to the dihedral angle of the hyperbolic prism. Then the statement is still you have isometric properties. So namely, this whole Riemannian polyhedron should be isometric to a parabolic prism in the hyperbolic space. Okay, so this is extension to the hyperbolic setting. Well, one natural question is, can we formulate such a conjecture or theorem for a positive lower bound of scalar curvature, where k is positive? Well, this turns out to be, I think, quite tricky, and I'll come back to this as with some observations at the end of this talk. Okay. Oh, by the way, this statement also holds for slightly more general polyhedral, which admits a degree 1 polyhedral map to P. Okay, so now I would like to mention some connections to between these conjectures to Riemannian general relativity. So as we all know now that Gromov, I think, proposed this conjecture or studied this property to study convergence of weak notions of scalar curvature and convergence property. Well, I would say it's a little bit frustrating to say, but at this moment, the use of this polyhedral comparison to study limit spaces where weak notion of scalar curvature has been quite difficult. On the other hand, it does have a nice connections with, for instance, Riemannian general relativity. So let's see some of those connections. So first observation is that the dihedral rigidity conjecture or theorem it's actually the localization of the positive mass theorem. So in the sense that if this dihedral rigidity conjecture holds for a single polyhedron P, then you can prove the positive mass theorem for symptotically flat manifolds in dimension n. Okay, so it's quite a simple observation. So because if you have a, let's say, a symptotically flat manifold, let's say X and G, this is asymptotically flat with non-negative scalar curvature, but not isometric to Euclidean space. But somehow you assume that the mass is negative. Then there is a famous low-com reduction, which says that you can deform the metric to a different one, G tilde, which is isometrically Euclidean near infinity. Still have non-negative scalar curvature, but not flat. Okay, so why this cannot happen? Well, you take this X and G, near infinity, it's a Euclidean, it's a Euclidean metric. So what you can do is that you can simply embed the boundary of your favorite polyhedron P inside near infinity. Okay, so this is boundary P. You rescale the Euclidean polyhedron to an extremely large polyhedron that encloses all this finite region. Near infinity, you isometrically embed. But now this boundary of P inside this asymptotically flat space will enclose some finite region. Now what you can do is that you can simply map this compact region K to a single point, and then let's call this region M minus K to P minus the point. So this is a degree 1 polyhedral map, right? So so the conjecture, dihedral rigidity conjecture should imply that this region M is isometric to Euclidean space, but which contradict your assumption. Okay, so once once you have the polyhedral comparison for a single model, Euclidean model, you do have a let's say a 5-line proof of the positive mass theory. Okay, so this is the first observation. Now, the second observation is that, likewise, the second theory, the second statement for, hyperbolic for hyperbolic models would imply the positive mass theorem for symptotically hyperbolic manifolds. Okay, so the second observation is that there's a nice connection between the polyhedral comparison and the Brown-York quasi-local mass. So let me maybe remind you of this notion of quasi-local mass. It's a classical theorem by Shi and Tam in 2002. So the theorem was saying the following thing. So suppose you take a smooth manifold with boundary, and you assume that its boundary omega has an isometric embedding into Rn as the boundary of a convex domain. Okay, so you have an omega, and you isometrically embed its boundary into the Euclidean space, and that bounds another region, omega 0, with the Euclidean metric. Okay. Now, suppose that your original boundary is mean convex, and the scalar curvature is non-negative in the interior. And then the statement would be the total mean curvature on the original manifold would be always less than or equal to the total mean curvature on the Euclidean embedding. Okay, with respect to the Euclidean metric. Okay, and you also have a rigidity phenomenon here. And that's to say that if they're equal, then the original Riemannian manifold with boundary is isometric to the is flat essentially. Okay. Okay, so the left-hand side of this inequality, the difference between the two total mean curvatures, is called the Brown-York quasi-local mass. So this is one of the notions of quasi-local mass that is designed to capture the total mass enclosed by a hypersurface in a symptotically flat manifold. All right, so the takeaway here is that for fixed domain, if you want to increase the scalar curvature, then you're going to decrease the boundary mean curvature. Well, it's kind of saying exactly the same phenomenon as the polyhedral comparison says, right? So because if you view the Riemannian polyhedron as a, let's say, as a varifold, then the total first variation, namely the total mean curvature in the weak sense of its boundary, is that is of course the is the integral of the total mean curvature on the smooth parts, and precisely the pi minus alpha j. This is the exterior dihedral, well, exterior angles along each edge times the length of the edges, right? So in other words, along the edges, the total mean curvature has this delta distribution of pi minus alpha j. Okay. Okay. So now I observed that lower dimensional singular strata does not contribute to mean curvature. So precisely the polyhedral comparison is sort of saying that if scalar curvature in the interior is positive, then somehow your total first variation on the boundary should not be bigger than the corresponding Euclidean total first variation. Okay. All right. So combining these two, if you think about this, what these things are saying, it's kind of tempting to say that can we, define quasi-local mass or mass using Riemannian polyhedral? It's a very nice observation. Actually, I think initiated by Penzi and Miao. And recently, they have this very nice result that basically says that Riemannian polyhedral can also be used to detect the ADM mass of an asymptotically flat manifold. So they have made several results, but I think this one that I'm describing is one of the best. So this is a joint work by Miao and Pubello last year. So you take any asymptotically flat manifold with some fall rate near infinity. In general, I think it's -1/2. And now you take any sequence of coordinate polyhedral that tends to infinity. So to describe this, you need to first fix a asymptotically flat Euclidean coordinates near infinity. And then under some natural degeneracy conditions, for instance, you need to assume that this family of pk goes to infinity in each direction, right? You can't just, they can't degenerate in some direction. So this mild and natural degeneracy conditions, then precisely if you compute the total boundary mean curvature and the total dihedral angle deficit compared to the Euclidean model, this quantity should converge to the ADM mass. Okay, so so in particular, in this theorem, the family of pk do not need to be of the same type. They can, be, you can start with a tetrahedron or a simplex, go to a cube, and even non-convex guys, and as long as they satisfy the non-degenerate conditions. Okay. And I find this theorem quite interesting because it's kind of a new perspective towards the positive mass theorem. And if you read the proof, it's also suggesting that, for instance, in the case of a cube, you can also relate these quantities in a cube by the slicings by a cube of one dimension lower. Okay, so it's kind of a reminiscent of the Schoen-Yau dimension reduction procedure as well. So I would like to see more directions, in development in this direction. Okay. And maybe let me also mention some recent development in the spinor approach. So this is a result in the recent paper by Wang Xian and Guoliang Yu, in December of last year. So they were also studying the same conjecture. Their theorem says that if you have you fix a Euclidean polyhedral with the Euclidean metric, and suppose it has some mild conditions, let's say non-zero Euler characteristic, and suppose you have a smooth Riemannian metric. So G is another smooth Riemannian metric, satisfies the scalar curvature non-negative, mean curvature non-negative, and the angle comparison. Then you would have the rigidity, a weaker rigidity phenomenon that R is 0, H is 0, and the dihedral angles are everywhere equal. So from here, it's easy to deduce that the metric G is actually Ricci flat. So in particular, it's flat in dimension 3. Okay. So I believe, I mean, I'm not an expert on the spinor approach, but I believe this is based on spectral theory manifolds with corners. And I heard that Professor Barr is going to give a talk in this seminar on April 22. So I'm looking forward to know more about this result and about the technique. And as we will see, I think one big advantage of the spinor approach in this conjecture is that it's going to be much easier if it works for higher dimensional simplices. As we will see in the minimal surface approach, for simplices will encounter certain regularity questions that people still find very challenging today. In fact, I think that, after I talked to several people, we think that the particular regularity question for capillary surfaces are kind of difficult. Okay. Anyway, so and any question so far before I move into a more technical part? Okay, great. So let's so I'll focus on the variational approach using minimal surfaces and calculus of variations for the rest of the talk. So to illustrate this idea, let's fix a simplex in R3, and let's suppose that you have something. So this is M, which looks like a curved Riemannian simplex, let's assume that scalar curvature non-negative, mean curvature non-negative, and everywhere the dihedral angle along M is equal to the corresponding dihedral angles of P. Okay, so this will simplify things a lot. In general, you can weaken these angle assumptions, but let's for now keep it to make things simple. Okay, so let's fix a vertex P and take the opposite face denoted by B. And there are three other faces, F1, F2, and F3. And what I'm gonna do is that I will try to construct a surface that corresponds to such a surface, separating surface in the Euclidean setting. Namely, in the Euclidean setting, you can take any parallel, so any plane parallel to the base to cut the Euclidean simplex into two regions, right? So the cutting surface here, as you can see, is a plane which intersect each of these side faces precisely at angle gamma j, because gamma j is the dihedral angle between the bottom and one of the sides. Okay, so in other words, I want to do the same thing and find such a surface in the Riemannian polyhedral. Okay, so once you realize that you need to do this, then there's a natural variational approach to construct such a surface. Namely, you will want to look at such a functional, which is the area of the separating surface and minus the some factor called cosine gamma j times the area that the surface cut along the boundary. Okay. Okay, so in the maybe it's easier to see it in a two-dimensional picture. So in this case, what I'm saying is that now you see that there are three numbers L1, L2, and L3. So the functional in this two-dimensional picture would be the length L1 minus cosine of gamma 1, let's say gamma 2 times L2, and minus cosine of gamma 3 times L3. Okay. Now, this functional is will achieve its infimum among all all separating surfaces. And let's take the infimum and take the separating surface to be sigma. Okay. Now the minimizer will always exist, and this is a result of the maximum principle. And the regularity in general is the difficult question, namely how many derivatives you can take on the graphing function of such a surface. Okay, but assume that the surface is regular, then it is a very nice surface. Namely, it's a minimal surface that meets all the side faces at constant contact angle gamma j. So precisely like the separating surface, by a parallel plane in the Euclidean simplex. Now, such a surface is it's called a capillary surface. So these guys are I think these kind of surfaces have a long history because they describe the surfaces in general of a liquid drop in the container. Okay, so people have studied them for over 200 years, and recently, and well, not much in geometry, but maybe more in analytic point of view in the past. Anyway, a simple case is that when the comparison model is a prism, these gamma j's are all pi over 2. So those cosine factors go away, right? So then the functional is just the functional of the area of the separating surface. In this case, you're just picking up the least area separating surface from the top to the bottom, okay? And of course, if the surface is regular, then it's a free boundary minimal surface meeting everywhere, meeting the ambient boundary at pi over 2 everywhere. Okay, so I'll just tell you some of the regularity result I've been able to prove. In 3 dimensions, the capillary minimizer is going to be C1 alpha graphical over its tangent plane everywhere. So the difficulty is, of course, the regularity near the corners. So away from the corners, the sigma is locally smooth. Okay, but near the corner, I believe C1 alpha is the best kind of regularity you can hope for. Okay, but this is enough because once you have such a surface, you can apply the Gauss-Bonnet formula and deduce what we want. Okay, so all right, and for the free boundary minimizer in higher dimensions, this is what we can prove, what I can prove with Nick Adler. So in these regular dimensions, if you have an n-dimensional non-obtuse prism, and you have a surface sigma, separating surface sigma is a free boundary minimal surface, then you can safely take the closure, and the closure is a C2 alpha graphical over its tangent plane everywhere. Okay, and this is precisely where the non-obtuse condition comes in. Okay. Okay, so the non-obtuse condition guarantees the C2 alpha, but if you only are willing to assume convexity, I believe your best hope is C1 alpha regularity instead. Now C1 alpha is also, seems also quite good, but for the inductive procedure I'm going to describe, it's safer to use C2 alpha instead. Okay. Anyway, so with this regularity results in mind, we can have this this argument. It's based on the Schoen-Yau dimension descent. So suppose you start with a counterexample of the theorem of dimension n. Then by looking at the corresponding functional, either capillary one or the free boundary one, you find a sufficiently regular, let's say a C2 alpha regular free boundary and minimizing hypersurface separating surface in the polyhedral. Then now using stability inequality, what you can do is that you can use the first eigenfunction of the associated elliptic operator in this stability to conformally deform the metric on the minimal hypersurface. And with this particular choice of the conformal factor here, the conformal metric will satisfy that the scalar curvature is non-negative, mean curvature is also non-negative. And since it's conformal, you're not changing the dihedral angle at all. So in other words, by doing this, you arrive at a counterexample of dimension 1 lower. Okay, so you basically just keep doing this dimension descent until you hit dimension 2, where everything goes to the Gauss-Bonnet. Okay. Okay, so there are some computational stuff, and then you still want the rigidity, but then the rigidity it's kind of a reminiscent of the Schoen-Yau torus rigidity, namely from the flatness of minimal surface, you can get the flatness of the entire polyhedron here. Okay, so here I used a previous result by Otis Chodos, Eichmeier, and Alessandro Carlotto. Anyway, so maybe let me say a word on how one extend this idea to hyperbolic polyhedrons in the case that the comparison model is what we call a parabolic prism in the hyperbolic space. So now remember the object we have is a guy sort of it's a Riemannian polyhedron like this. And you have this special direction x1. And what we assume here is that the mean curvature on top is larger than n minus 1, and on bottom is larger than n minus of n minus 1. Okay, and on the sides they're all mean convex. So instead of looking at the free boundary energy, you look at the following energy. So what I would like to do here is that I will try to find a separating surface. Let me use red here. The separating surface should satisfy that the mean curvature is precisely n minus 1. Okay, so to do that, what you do is that you basically minimize the well, you can call it the BPS Brownian action by physicists, but for mathematicians, this is like the isoperimetric function. Okay, to find an isoperimetric surface. And by some computation, you will the dimension reduction argument, the separating surface you find in this way will violate the Euclidean space. Well, the dihedral rigidity theorem for the Euclidean model modeled on a triangle in this picture. Okay. Okay, so this is roughly speaking how the variational approach work here. I do want to well, maybe before I move on, any questions so far? Okay, great. So then let me maybe describe a little bit of the questions that I find interesting and quite mysterious. So the first question is, how do we characterize, for instance, the scalar curvature bounded below by a positive constant? Now, of course, the model space you would like to say is, well, it is the some polyhedron in the sphere, right? But now, given the connection between the dihedral rigidity conjecture and the positive mass theorems, we all know that the corresponding positive mass theorem for the spherical model spaces are quite delicate. Because, for instance, there is this mean O conjecture where we do now have counterexample, right? So basically, Brandon Marcus Nevis says that the corresponding scalar curvature rigidity statement on a hemisphere does not hold. Okay. So one way to make the comparison work would be to cook up a standard to look at the standard spherical simplex, namely the intersection of the sphere with these coordinates, ambient coordinates being non-negative. So with this in mind, well, one can formulate a conjecture as follows. So suppose you have a Riemannian simplex such that the scalar curvature is larger than or equal to the one on the sphere. And let's say the faces are piecewise totally geodesic, so it's a much stronger condition, but we can start from here. Okay, and suppose that the dihedral angle is everywhere non-obtuse. Now the dihedral angle between these spherical standard spherical simplices are everywhere pi/2. Okay, so now we assume in the comparison model it's non-obtuse, and then let's assume that the faces are piecewise isometric to a intrinsically isometric to a standard spherical sphere simplex of one dimension lower. Then whether it's true or not that the Riemannian simplex is isometric to the standard spherical simplex omega n. Okay, so this is the question. Now there are some, previously I mentioned that there is this counterexample by Brandon Marcus Nevis that the scalar curvature rigidity statement does not hold on a hemisphere. On the other hand, it is known that such a statement holds for a spherical cap of a small size. Okay. Now, interestingly, if you look at the size where this spherical rigidity statement holds, this size, that sphere is precisely of the same size of the inscribed sphere of a spherical simplex. Namely, what I'm saying here is that, on the spherical, standard spherical simplex, you can inscribe the largest spherical cap there, right? So I believe that this size here, the size of this spherical cap is of the same order with the theorem, another theorem that the scalar curvature rigidity holds. Okay, so it is an evidence that this conjecture may be true. And of course, we have the almost rigidity conjecture that's an analogy of the torus rigidity conjecture from Christina. So I think the state one possible way to formulate it is that, let's say we take a three-dimensional cube and a sequence of smooth Riemannian metric such that scalar curvature almost non-negative. But let's assume that mean convex and angles are smaller than or equal to pi/2. Then under volume upper bounds, diameter upper bound, and some kind of condition, let's say the minimal area of the least area, minimal surface is bounded below, then how does this sequence of cubes converge? I think this is one, it's a localized version of the torus rigidity question. I think the answer to one will likely, give the answer to the other. Okay. So maybe let me stop here, and thanks for the attention.